May 1945. The thousand-year Reich has collapsed into a landscape of twisted girders and crushed masonry. Across the shattered industrial zones of the Ruhr and the subterranean galleries of the Harz Mountains, the machinery of vengeance has fallen silent. The V-1 flying bomb, Hitler's Vergeltungswaffe I, is no longer a terror weapon raining down on London. It is now the most sought-after commodity in Europe. While the public celebrated victory in the streets of London and Paris, a different kind of war had already begun in the shadows. This was not a war for territory, but a desperate race for intellectual property. The victors, American, Soviet, British and French technical intelligence teams, descended upon the German research facilities like vultures picking at the carcass of the Luftwaffe. The most dramatic act of this technological looting took place deep within central Germany, at the Mittelwerk underground factory near Nordhausen. This was the dark heart of the V-weapon production, a place built on the suffering of slave labor. By May, the American 3rd Armored Division had secured the site, but a geopolitical clock was ticking. The Yalta Conference had designated Thuringia, where the factory lay, as part of the future Soviet occupation zone. The Americans had weeks, perhaps only days, to strip the facility before the Red Army arrived. Under the auspices of Operation Paperclip, U.S. Army ordnance teams staged a heist of continental proportions. They did not merely take notes, they emptied the larder. In a fevered operation lasting weeks, American troops loaded 341 railcars with V-1 and V-2 components. They took the fuselages, the gyroscopes, the tooling jigs, and the unfinished engine cowlings. They crated up tons of technical documents. When the Soviet forces finally rolled into Nordhausen in July 1945, they found the underground galleries largely swept clean. The Americans had taken the hardware. The Soviets, however, would take the men. In a parallel operation known as Operation Oswiakim, Soviet NKVD units would later round up thousands of German technical specialists at gunpoint in the middle of the night, shipping them east to jumpstart Stalin's missile program. The V-1 was crude, noisy, and inaccurate. By 1945 standards, it was almost obsolete. Yet for the next decade, this simple, ugly machine would become the progenitor of the modern cruise missile. It would teach the superpowers how to build the weapons of the next war. This is the story of what happened to the V-1 after the firing stopped. Before the V-1 could be reborn in the laboratories of the superpowers, the sheer physical bulk of the German arsenal had to be dealt with. The Third Reich had produced approximately 30,000 V-1s. While thousands had been fired at England and Belgium, thousands more sat rotting in railway sidings, hidden forest depots, and salt mines across occupied Europe. In the British and Canadian occupation zones of Schleswig-Holstein, the disposal of these weapons became a logistical headache. Allied commanders were terrified that die-hard Nazi werewolf units might try to launch a final terror strike. The order was given to destroy them. Under the supervision of the Royal Engineers, vast pits were dug in the countryside. V-1 fuselages, stripped of their valuable gyroscopes, were stacked like cordwood. Demolition charges were applied, and the weapons that had once terrified London were turned into scrap metal in controlled detonations that shook the German earth. In the Netherlands, the situation was even more precarious. The Germans had used the Dutch coast as a primary launch site. As the Wehrmacht retreated, they booby-trapped the bunkers. Dutch Explosive Ordnance Disposal, EOD units, spent the late 1940s combing the dunes for hidden caches. They found hundreds of V-1s in camouflaged concrete shelters, their fuel tanks still loaded with volatile, high-octane petrol. There was also a lingering, ghostly hazard from the war years. Not every V-1 launched had reached its target. Many had failed on launch or splashed down into the North Sea and the English Channel. For years after the war, corroded V-1 airframes would wash up on the beaches of Kent and Normandy, tangled in seaweed, a rusting reminder of the blitz that required immediate and dangerous intervention by bomb disposal squads. The United States did not wait for the war to end to appropriate German technology. In July 1944, mere weeks after the first V-1s struck London, American recovery teams were already scavenging parts from unexploded duds in English potato fields. These twisted scraps of mild steel were crated and flown to Wright Field in Ohio. The order from General Arnold was simple: copy it, then mass-produce it. The result was the Republic Ford JB2, known as the Loon. To the untrained eye, it was identical to the German Fiesler Fi 103. But to the engineer, the difference was profound. The German V-1 was a product of desperation, riveted together by starving slave labor, often with inconsistent tolerances and sabotaged guidance units. The American Loon was a product of Detroit. Ford Motor Company took the crude Argus AS-014 pulse-jet engine and applied American automotive mass production standards. The German engine cowlings were often hand-fitted, requiring filing and hammering to seal. The Ford PJ31 engine was standardized to within 1/1000th of an inch. The fuselage, originally a mix of steel and plywood in late-war German models, was rendered in welded low-carbon steel by Republic Aviation. Crucially, the Americans revolutionized the launch physics. The Germans had relied on a complex steam catapult system powered by the violent chemical reaction of T-Stoff and Z-Stoff, hydrogen peroxide and calcium permanganate. It was volatile, corrosive, and prone to exploding on the ramp. The Americans abandoned this chemical nightmare. Instead, they designed a zero-length launch sled powered by 4 solid-fuel rockets. It was safer, faster to set up, and reliable in all weather conditions. By 1945, the U.S. Army Air Forces had planned to unleash a barrage of these American V-1s against Japan. The invasion plan, Operation Downfall, called for thousands of JB-2s to be launched from the decks of escort carriers and from captured islands, saturating the Japanese mainland before any GI set foot on the beaches. The atomic bomb rendered the invasion unnecessary. Suddenly, the U.S. military found itself with thousands of Loons and no target. Production ceased after approximately 1,385 units had been built. But the program was not scrapped, it was repurposed. The JB-2 became the primary testbed for the dawn of the guided missile age. At the White Sands Proving Ground in New Mexico and the naval test ranges at Point Mugu, California, the Loon was used to solve the fundamental problems of missile flight. The Germans had used a simple autopilot, a master compass and a pair of gyroscopes. It could keep the bombs straight and level, but it couldn't correct for wind drift or complex terrain. American engineers gutted the Loon's crude guidance and installed the first generation of command guidance systems. One notable series of tests in 1946 at Point Mugu saw a JB-2 launched and then controlled remotely by a bombardier sitting in the nose of a B-17 mothership, flying miles away. Using a joystick and a UHF radio link, the operator steered the missile into a mock target ship. This was the birth of the command link technology that would eventually define drone warfare. By 1946, the Loon had become more than a test subject. It was a pawn in a bitter inter-service rivalry. The post-war American military was shrinking, and budgets were being slashed. The newly formed United States Air Force and the U.S. Navy were locked in a fierce battle for relevance and funding. The JB-2 Loon sat squarely in the middle of this war within the Pentagon. The Air Force viewed the Loon as a pilotless bomber, a tactical extension of their artillery that could strike land targets without risking air crews. They wanted to deploy it in mobile squadrons across Europe to counter the Soviet tank threat. The Navy, however, saw the future differently. They wanted the Loon for carrier operations and submarine strikes. They argued that a ship-launched cruise missile was the ultimate power projection tool, capable of hitting inland targets from international waters. This doctrinal clash, who owned the guided missile, led to duplicated efforts, wasted resources, and intense political maneuvering in Washington. Both services fought tooth and nail for custody of the German orphan. While the generals argued in Washington, the Navy undertook a perilous experiment at sea, taking the pulse jet underwater. The Navy recognized the potential of a submarine-launched cruise missile. They designated the naval variant the WW2. The challenges were immense. A V-1 was not designed to be submerged. To solve this, the Navy utilized the USS Cusk and the USS Carbonero, submarines specially modified with a watertight, cylindrical hangar on the aft deck. The operational procedure was a ballet of high-risk engineering. The submarine would surface, and the crew would rush onto the wet deck. They had to open the hangar, drag the missile out on rails, assemble the wings, which were stored separately, attach the solid rocket boosters, and fuel the pulse jet, all while bobbing in the Pacific swell. In 1947, off the coast of California, the USS Cusk made history by conducting the first launch of a guided missile from a submarine. The roar of the pulse jet over the water was deafening, the flame from the booster rockets scorching the submarine's pressure hull. The KGW-1 flew over 20 miles. However, the vibration of the pulse jet proved to be the undoing of the naval program. The acoustic hammering was so severe that it shook the submarine's own radar masts and radio antennas loose. Furthermore, the highly volatile aviation fuel required for the missile was a terrifying hazard to store inside a submarine. While the KGW-1 never saw combat, it proved the concept was viable. The lessons learned on the decks of the Cusk flowed directly into the development of the SSMN-8 Regulus, a nuclear-armed turbojet cruise missile that would patrol the Pacific in the 1950s. While the Americans were applying mass production to the V-1, the Soviet Union was struggling to master it. For Joseph Stalin, the V-1 was not just a weapon, it was an embarrassment. The fact that fascist Germany had possessed a robot bomb while the Soviet Union relied on conventional artillery was unacceptable. The Kremlin demanded a Soviet equivalent, and they demanded it immediately. In 1944, captured V-1s from the Blizna test range in Poland were shipped to Moscow. The task of reverse engineering them fell to a young, ambitious engineer named Vladimir Chelomey. Chelomey faced challenges the Americans did not. Soviet metallurgy in 1945 lagged behind the West. The high-temperature steel alloys required for the pulse jet's shutter valves, the flimsy metal gates that opened and closed 50 times a second to let air in, were difficult for Soviet industry to replicate. In early ground tests during 1945, several prototype engines exploded catastrophically when the valves shattered, sending shrapnel through the test stands. The program was nearly derailed until Chelomey managed to source better alloys from captured German stocks, essentially cannibalizing the enemy's supply chain to build his own weapon. The Soviet copy was designated the 10KH. Chelomey did not work alone. Following the mass deportations of Operation Osoaviakhim in 1946, hundreds of German aviation specialists found themselves isolated on Gorodomlia Island, located in Lake Seliger, roughly 200 miles from Moscow. This was a golden cage. The Germans lived in relative comfort compared to the Soviet population, but they were prisoners nonetheless. Among them were engineers from the Junkers and Heinkel firms, who had intimate knowledge of pulse jet dynamics. The Soviet leadership, driven by a mix of pragmatism and paranoia, forced these men to troubleshoot the failing 10KH program. It was a tense collaboration. The Germans provided the theoretical math to fix the vibration issues, while Chelomey took the credit in Moscow. Early flight tests were disastrous. The 10KH suffered from the same stability issues as the German original, but exacerbated by manufacturing defects. The wooden wings, used to save aluminium, often delaminated in the humid air of the test ranges or shattered under the acoustic pounding of the pulse jet. Gyroscopes failed. Autopilots drifted. In several test launches from PE-8 bombers, the missiles simply refused to start, tumbling ignominiously to the ground. Yet the Soviets persisted with a grim determination. They viewed the 10KH not just as a weapon, but as a university for their engineers. They built improved versions like the 14kh, which in 1947 trials achieved a range of nearly 300 kilometers. They pushed further with the 16kh, a radical variant that experimented with twin engines and air launch capabilities from Tu-2 bombers. These experiments deeply influenced later Soviet designs, like the KS-1 Comet. While the 10kh never entered squadron service as a strategic weapon, the project secured Vladimir Chalamet's future. His success in eventually taming the pulse jet earned him Stalin's favor, allowing him to establish his own design bureau, OKB-52. This bureau would go on to dominate the field of anti-ship missiles. In the devastation of post-war Europe, the V-1 found a diverse set of new masters. Great Britain, having endured the impact of over 2,400 V-1s on Greater London alone, was keen to understand the weapon that had tormented its populace. In the immediate aftermath of the surrender, the British military launched Operation Backfire. At Cuxhaven in Germany, British troops, supervising captured German ground crews, assembled and fired V-1s out to sea. This was not merely for ballistics data. It was to train British radar operators on how to track high-speed, low-level targets. By the 1950s, the tables had turned completely. The Royal Navy and the RAF began importing French-built copies of the V-1 to use as live-fire targets. In a supreme irony, British anti-aircraft crews practiced their aim by shooting down the very silhouette that had terrorized their capital a decade earlier. It was not always a simple task. In one notable incident in 1954, a target drone evaded anti-aircraft fire for over 20 minutes due to unexpected wind drift, exposing glaring flaws in NATO's low-level air defense grid. France, eager to rebuild its shattered aviation industry, seized upon the technology with vigor. The Arsenal de l'Aéronautique employed captured German engineers to refine the design into the Arsenal Arcero CT-10. The CT-10 was the V-1 domesticated. The French conducted extensive testing in their North African colonies, specifically at the Colombe Béchar range in Algeria. The harsh desert environment provided a new set of data points. The extreme heat affected the thrust of the pulse jet, and sand ingestion proved to be a constant maintenance headache. Yet the French persisted. They recognized that the pulse jet's vibration made it a poor weapon, but its low cost made it an excellent target. Over 2,000 CT-10s were produced, a massive run for the era. They were so successful that they were exported back to the United States Navy for target practice, completing a strange transatlantic circle of technology. Sweden took a different path. The Swedish Navy, looking at the threat of the Soviet Baltic Fleet, saw the potential for a ship killer. They developed the RB-310 and RB-315. These were not direct clones, but spiritual successors, utilizing the pulse jet concept for short-range anti-ship strikes. However, during tests in the Baltic Sea in 1958, the Swedes discovered a critical vulnerability. The loud, radar-reflective intake of the pulse jet made the missile incredibly easy to spot on radar and susceptible to electronic jamming. The pulse jet was a dead end. By the late 1950s, Sweden, too, moved to turbojet-powered missiles like the RB-08. Why did the V-1 lineage die out? Why don't we see pulse jet cruise missiles today? To understand this, we must look inside the engine, at the metallurgy of failure and the physics of sound. The heart of the Argus 014 engine was the shutter valve matrix. Located at the front intake, this grid of small steel flaps operated like a set of Venetian blinds. They opened to let air in and slammed shut when the fuel ignited, forcing the explosion out the back. This cycle happened 45 to 50 times per second. The physical stress on these valves was catastrophic. In post-war evaluations, Allied metallurgists found that the constant hammering and extreme heat, cycling from cold air to 1,000 degrees Celsius in milliseconds, caused the steel to lose its temper and fatigue. The average operational lifespan of a V-1 valve grid was less than 1 hour. This was acceptable for a weapon designed to fly for 40 minutes and then explode. It was unacceptable for a military that demanded reusable assets. Beyond the vibration, there was the noise. The pulse jet was an acoustic monstrosity. In operation, it produced a sound pressure level of between 130 and 150 decibels. This was not merely loud, it was physically debilitating. Ground crews working near the launch ramps frequently suffered from nausea, vertigo, and burst eardrums, even with ear protection. But militarily, the noise was a fatal flaw. A V-1 launch could be heard from over 30 miles away. In an era where radar was becoming ubiquitous, the V-1 announced its presence like a thunderclap. It eliminated any possibility of stealth or surprise. A battery of pulse jet missiles could never be hidden. The moment they fired, every acoustic detector in the theater of war would pinpoint their location instantly. The economics were seductive. A pulse jet engine cost roughly $215 to manufacture in 1945 money, compared to over $5,000 for a turbojet of equivalent thrust. But the performance penalty was severe. The pulse jet achieved the equivalent of just 1 to 2 miles per gallon. To fly faster and farther, the engine had to be larger, which increased drag and fuel consumption in a vicious cycle. Modern hypersonic missiles use ramjets, which breathe air like a pulse jet but burn fuel continuously, avoiding the violent intermittency of the V-1. The V-1 was a weapon of total war, designed to fly once and die. In the post-war world, where militaries demanded reliability, precision, and reusability, the pulse jet was simply too crude. The V-1 flying bombs that survived the war did not end up as weapons. They ended up as teachers. They were flown until they fell apart, dissected by men who would go on to build the arsenals of the Cold War. We can trace a direct, unbroken line of mechanical DNA from the V-1. The data gathered from the WW2 Loon directly informed the design of the Martin MGM-1 Matador. The Matador evolved into the MGM-13 Mace, which featured terrain-matching radar. The lessons of the Mace were refined into the AGM-86 and eventually the BGM-109 Tomahawk. When a Tomahawk strikes a target with pinpoint accuracy today, it is the great-grandchild of the crude, buzzing terror of 1944. In the East, the lineage is equally clear. Vladimir Chelomey's struggles with the 10KH taught Soviet engineers how to manage airflow and separation. This knowledge was poured into the P-5 Tyaturka, a turbojet cruise missile that terrified NATO admirals, and ultimately into the P-700 Granit, the massive shipwrecking missile of the Soviet Navy. Even the concept of the cheap expendable has returned. Today's loitering munitions, the so-called suicide drones like the Switchblade or the Shahed, are the spiritual successors of the V-1. They rely on the same ruthless calculus, a cheap, mass-produced airframe sent on a one-way mission to destroy a high-value target. There is a final, quiet footnote to the V-1 story. In the early 1950s, a handful of stripped-down V-1 airframes were used at White Sands not as weapons, but as meteorological probes. Launched vertically, they carried sensors into the upper atmosphere to measure wind shear and air density. Before they were scrapped, these machines of vengeance spent their final moments providing weather reports for the peaceful exploration of space. Today, over 20 intact V-1s reside in museums worldwide, from the Smithsonian in Washington to the original test sites at Peenemünde. They stand as silent, rusting sentinels. Their pulse jets are silenced, but the lessons they taught the world are still flying overhead, unseen, in the stratosphere. The V-1 failed to save the Third Reich, but in the laboratories of its conquerors, it succeeded in changing warfare forever.